Hello and welcome to another self-study session. Today we're going to be looking at Leetcode number 300, the longest increasing subsequence. So with this problem, we're given an integer array nums, and our task is to return the length of the longest strictly increasing subsequence. A subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. So for example, given an array with elements 3, 6, 2, 7, it is a subsequence of the larger array with elements 0, 3, 1, 6, 2, 2, 7. The longest increasing subsequence, however, would be an array with elements 0, 1, 2, 7, or another array with elements 0, 3, 6, 7. And these are increasing subsequence arrays because the order of the elements in the arrays are in ascending order. So how do we go about solving this problem? Well, the naive or natural way of solving this problem would be to look at each element of the array as a target and then scan to the right of the target in search of an element that is greater than the target. When an element is found that is greater than the target, we add 1 to the length that we already have, and then the element that is greater than the target becomes the new target. And then the algorithm would continue in this fashion for every element in the array until the end of the array. So looking at this as an example, starting at index 0, we see that we have a value of 10. When we scan to the right of 10, we find that 20 is greater than 10. And so we add 1 to the length that we already have, which is 1. And it should be noted that each element in the array is itself a subsequence with a length of 1. So ideally, we want to keep track of these lengths. And so 1 plus 1 will be 2. And so the max in this event will be 2. We continue on to index of 1. We scan to the right of index 1. We'll find that 20 is greater than 9. We add 1 to 1. We'll get 2 again. And so max of 2 and 2 is still 2. We proceed. We're now at index 2. And we scan to the right of 2. And we see that 3 is greater than 2. So we add 1 to 1. We get another length of 2. 3 now becomes the new target. We scan to the right of 3. 8 is greater than 3. We add 1 to that 2. We get a length of 3. So our new max length is now going to be 3. And now 8 is also going to be the new target. We scan to the right of 8. And we see that 20 is greater than 8. And we add 1 to that 3. We're going to get a max of 4. And so the algorithm will proceed this way, beginning at index 3. Scan to the right, it's going to get a length of 3. Beginning at index 4, it's going to get a length of 2. And the final element in the array is always going to have a length, beginning at the final element is always going to have a length of 1. And so what do we notice is the problem with this particular solution? It works for a really small input. But however, what we notice is that we are repeatedly looking at these values. So when we started at index 0, we went all the way down to the end of the array. We looked at from index 1, we went all the way down. And so even though it's getting smaller and smaller, we are still revisiting, elements in the array. And so this works for smaller inputs, but it is not very ideal for a larger input array. However, we're still going to look at it in code. We would need an outer loop for each target. We will also need an inner loop for the scanning against the target. And the way we're going to solve this is through recursion. And so we're going to have a recursive call for every new target, for every new input set, and that's going to add an additional overhead. So you can see how quickly the time complexity of this algorithm just gets worse. Anyhow, we're still going to look at it in code and see what this looks like. So let's head over. So let's see what this looks like in code. We have our variable for storing the length of the array. If the array is empty, we simply return 0 as our length. We have a memo variable here. It's an array of the same length as the input array, and each element in this array is filled with a value of 0. We fill with a value of 0 because we need to run a check here, and if the memo at start index is not equal to 0, we simply return that memoized or cached solution. We have our variable here for keeping track of the max. If now the start index is equal to the length of the array minus 1, we simply return that start in that memoized solution at start index. That's our our base case. And now we have our two loops here, the outer loop for the target and the inner loop for the values that we're going to be comparing against the target. If we find a value that is greater than the target, then we're going to enter that condition. We're going to add 1 to add on to our length, and we're going to make another recursive call beginning at the index of the element that was found, which was greater than the target. So we have this count the parameter here, and it starts at that index. We need to run a check, but actually it's only until these recursive calls are returned do we actually store anything in memo. So yes, we're gonna run a check to see if what we have previously is larger or vice versa, and it's gonna update accordingly. Here we are continuously checking for our new max on line 72. We're gonna return memo at the start index. Simply just returning the memoized solution at the given input, right? This is our initial call starting at index 0. Here we return max plus 1, and it's plus 1 because each element in the array is itself a subsequence. So let's run this. So this is our array that we have been using throughout the slides. Let's run that. We see that we have our value of 4 as our length. Now we see that this works just fine for really small inputs, but what if the input was larger? And here we're going to use 2500 as our array size. So it just runs from 0 to 22,499 actually, because it's less than, but it's going to be a size of 2500. So let's run this one, and we see that it's taking a really long time. So let's just cancel that out, and let's lessen this. And it's also taking some time. So let's continue to make it smaller. Still taking time. Let's cancel that out. And okay, there we go. We finally returned something, but it still took a really long time, even with just a size of 1000. So this solution is definitely not ideal, and it would not pass Leetcode due to a time limit issue. So it is, however, good to know this particular top-down approach via recursion, because then it gives us insight on how we can go about improving this particular algorithm, and where tabulation or a bottom-up approach would be better suited in this case. So let's head over and look at tabulation. So with tabulation, we have an additional array, all populated with a value of 1, and that is because, as we mentioned earlier, each element in the array is itself a subsequence. So we loop through the array, the input array, in an inner loop, or the right index pointer. If the element at the right index is found that is greater than the current element at the left index, we take the accumulated value in the table of the left index and add 1. We determine if this new value is greater than the table value of the right index, and if the above is true, we update the table of the right index. So let's look at this with an example. We have our input array, we have our table, all pre-populated with values of 1. And as we mentioned earlier, they're filled with 1s because each element in the array is itself a subsequence with a length of 1. We have I, it's our outer loop or left index pointer. We have j, it's our inner loop or right index pointer. So when I is equal to 0, j is equal to 5, we have 20 being greater than 10, and we take what we have at I, add 1, and then we compare it to what we have at j in the table. And so we add 1, we get 2, max of 2 and 1, which is what we originally have. We're going to get a 2, and so 2 is going to become the new value at j. When I is equal to 1 and j is equal to 5, we're going to have 20 is greater than 9, and so we're going to add 1 to what we have at I, which is going to be 2, and we already have a 2 here, so max of 2 and 2 is still going to be 2. When I is equal to 2, I is equal to 2, and j is equal to 3, we're going to have 3 is greater than 2, and so we're going to take what we have at I, which is 1, at 1, we're going to get 2, and we're going to compare it to what we have at j originally. And what we have at j is 1, so 2 is going to become the new value. And then when j is equal to 4, we're going to have 8 is greater than 2. We add 1 to what we have at I, which is going to be 2, and 2 is greater than what we have at j. We have at j is a 1, and so 2 is going to become the new value at j. And then when j is equal to 5, 20 is greater than 2. We're going to add 1 to what we have at I, which is going to be 2 again. And since it's already 2, then a max of 2 and 2 is still going to be 2, right? When I is equal to 3, this is our original array. J is equal to 4, 8 is greater than 3. We're going to add 1 to what we already have. What we already have is a 2, plus 1 is going to be 3. And what we have at j is a 2, so max of 3 and 2 is 3. When j is equal to 5, 20 is greater than 3. We're going to add 1 to what we already have, which is a 2. Add 1 is going to be 3, and 3 is greater than 2, what we originally had at j, and so 3 is going to become the new value at j. When I is equal to 4, this is our original array. I is equal to 4. We're going to add 1 to what we already have. It's going to be a 4, and 4 is greater than what we originally have at j, so that's going to become the new max value. When I is going to be equal to 5, now there's no way for j to go, so that's the end of our loop. And once we are keeping track of this max value, we simply return that max value. And so that's it. And let's head over into the code and see what this looks like. So what does this look like in code? We have our method here. We have our variable for the length of the input array. If the array is empty, we return 0. We have our table with the size of the input array, and each value is filled with 1. And the max is also set as 1. That is because each element in the array is itself a subsequence with a length of 1. We have our loops here, our outer loop and our inner loop. So whenever a value in the inner loop, whether on the right, is greater than the value in the outer loop, the left or our target value, we enter that condition. We add 1 for the new length that we found, added to what we've already accumulated so far. We run a check if this newly calculated value is greater than what we already have, and it's updated accordingly. On the next line, we're just simply keeping track of our max value, and once we're done, we return that max value. And so if we run our example that we've been speaking of, we get 4. 1, 2, 3, 4. If we run the next example, we get 5, 1, 2, 3, 4, 5. And that's really it. I have another version here, but the loops are different. It starts with a smaller window and then increases. But the rest of the algorithm is pretty much the same. We return the max. Let's say we weren't keeping track of the max. We could just sort that table out and return the last value. But this adds additional time to the solution, so it's better to just keep track of the max value. And that's pretty much it for this. We can run the same run it, and you can see that it actually produces the same result. And if you test this in Leetcode, they're pretty much the same in terms of time complexity. So you can try it out on your own. So that's pretty much it. Yep. I almost forgot. Let's try our more optimized solution with the large input. Let's run that. And there we go. You see how quick that was compared to last time? Hey, let's bring this back up to 2500. Look at that. Whew. Hey, let's try 5000. Yep, it's good. It's good. So we've shown that we can solve this problem of longest increasing subsequence using a top-down approach via recursion. However, even with memoization, this solution would not be ideal. The recursive solution, that is. We've illustrated that given a really large input array, the result would be slow to return. And ideally, what we want to use is a solution like tabulation, whereby we use values that we've already accumulated or stored in our table to further solve the remainder subproblems. And that's it for that. If there's anything at all that I missed, please let me know. And if you like this, or if it was useful to you at all in terms of understanding how we arrived at this tabulation method, this more efficient tabulation method, please let me know in the comments below. Do like and subscribe, and I'll see you around on my next session. So take care and thanks again. Ciao.